Okay, so this is going to be week 6, day 1. There's no lecture for Wednesday because we have the test. So to summarize last class, we were talking about, or at least the end of the last class, we were talking about 5 properties that binary trees have. And we ran out of time and didn't talk about that last property in detail. So the property says, in a binary tree where every node has 0 or 2 children, number of leaf nodes is always going to be one more than the nodes with 2 children. So leaf nodes are the ones that don't have children. And then internal nodes are nodes that have children. And of those internal nodes, we are saying that there's always going to be one less than the number of leaf nodes, or one leaf node more than the number of nodes that are internal that have 2 children. So, an example. Suppose that we have the following 3. This one and this one are internal nodes. Then these 3 are leaf nodes. This guy and this guy, both of the internal nodes in this case happen to have 2 children each. So as you can see, there's 3 leaf nodes and there's 2 internal nodes with 2 children, which is what that property is saying. Let me give you another example. The same thing, but now we have a node there. Technically, there are 3 internal nodes, of which 2 of them have 2 children. One of them has 1 children. Can you all see which ones are those? This one and this one are the 2 children nodes, internal ones. This one is the internal one that has 1 child. And there are still only 3 leaf nodes. And this is yet again saying the number of internal nodes with 2 children is the leaf nodes minus 1. So that's 3 minus 1, which is 2, which happens to be the answer too. So just basically, it's not exhaustive to show you 2 examples. I don't want to do the proof, but it's just something useful to know. Okay, so that was the last property that we didn't get to cover last time. Okay, so now I'm going to go ahead and create a brand new file for today. So the next topic that we're going to talk about is going to be a couple of different types of binary trees. Just more some jargon, I suppose. We have what is known as a full binary tree. And these are just common types of binary trees, okay? That will be the general topic, I suppose. Hold on, this is shaking. Common types of binary trees. And I really wish I could abbreviate binary trees, but if I say B trees, it's a completely different data structure, so can't really do that. Okay, so we have a full binary tree. So what's a full binary tree? Well, a full binary tree, we consider a binary tree to be full when every node has 0 or 2 children. So there cannot be any 1 children nodes in a binary tree. Okay? So let's just write that here. So a binary tree is full if and only if every node has 0 or 2 children. Let me give you some examples of that. So here we have, for example, a binary tree that will be considered full. Because every node has 0 children, which in this case, every leaf node has 0 children. So, these guys. That's why they're considered leaf nodes. And then the other internal nodes, which are those 3, have 2 children, right? This guy has this and this guy has this and this guy has this and that. So all 3 of them have children. Here's another example that you can see. That's also considered a full binary tree, because even though it doesn't look very nice, and of course the mirror of that is also the case, This has two children, two children, two children, 0, 0, 0, 0. That covers all of them. Yes?
So like, is the root node allowed to have more than 2 nodes, or that's it?
So the question is the root node is allowed to have more than 2 nodes? The answer is it depends on what tree you're talking about. This is a binary tree. So any node, not just the root node, but any node cannot have more than 2 children.
Okay.
So the special cases of, for example, that's technically a binary tree, and that's also a full binary tree. This, a single node, can also be considered a full binary tree because it's just one node and it's a leaf node. And this gets a little mathematic, but there's also the case of just nothing, no nodes at all. That's technically like an empty set, so it gets a little iffy, like especially when you think about what is the height of such a tree. So yeah, but for all intents and purposes, because it's a binary tree, it can have 0, 1, or 2 nodes. But if it's a full binary tree, it can have either 0 or 2. So the following would not be a full binary tree, with the root of just having a single node. So yeah, that's pretty much what full means. And then a nice thing to know is that in a full binary tree, the number of leaf nodes is the number of internal nodes plus 1. That's just a nice thing to know. So number of leaf nodes is equal to the internal nodes plus 1. That's saying here we have 2 leaf nodes, and then we have 1 internal node. So if you see 1 plus 1 is 2. Here we have 1 leaf node and 1 internal node. However, this one is not a full binary tree because it would need a child here. So that's why that breaks on that one. So no panic there. This, however, is a full binary tree. So here we have 1, 2, 3 internal nodes and 4 leaf nodes. So as you can see, that property only holds for full binary trees. Okay, the next term. These are all kind of, it's like they're trying to sell you a car. You got a full set, and then you get the complete set. And then there's going to be the perfect set. So
what about the perfect set S?
There's perfect as well. Yeah, there's a perfect binary tree that I'm about to cover. So like, yeah, so get scammed. Anyways, complete binary tree. What's a complete binary tree? Well, a binary that is going to be. I'm just going to write it. It's a binary tree. Where all levels are completely filled, except possibly, a lot of adjectives here, the last level. However, if that is the case, that the last level is not full, then that last level has to have all the keys or all the nodes as left as possible. Okay, so so a binary tree, remember what levels is, I guess? First, maybe we should refresh that. We consider this level 0 or level 1, depending on whose book you're reading. If we're going with level 0, then this is level 1, and this is level 2. If we're going with this level being level 1, then this will be 1, 2, 3. It's like British versus American in terms of like floors, right? So ultimately, we are saying that all the levels except the last level have to be full. And by full, we're saying that if it's a binary tree, they have to have 2 children. Now, the last level doesn't have to be full. It can be partially full. But in that case, such as here, they have to be moved all the way to the left as possible, which means that this is technically not a complete binary tree. To make it complete, I would have to, actually here it's just easier to draw it again. To move 1 node, I would have to move this node from where it currently is over here into that spot. Now it will consider a complete binary tree. Here's the thing though. If this is a binary search tree, then suppose that this was something like P and Q. I can't just move it like that because I break the property, right? So I have to do some sort of rotations. So I actually have to change the order of them and make it into Q, P, like that to fix it. And that may break other things on its own. So, yeah, we'll talk about rotations later on. But it's not sometimes so easy. But anyways, it's considered complete when everything but the last level, so the leaf nodes, are not full in the sense that they have the maximum amount of children, and then the last level, they have to be all the way to the left. This will come in useful when we talk about heaps, because heaps have this property. So when we do heap sort of that thing, which will be quite a while from now, though a heap is going to always be a complete binary tree. And that's very nice too when we're dealing with implementation, like in an array. So that's all I'll say about that one for now. Technically, this is also a complete binary tree, just a single node, I suppose. Is this a complete binary tree? Yes, because everything but the last level is full. And that last level, the only node is all the way to the left. So it's actually complete technically. If I add this node, it's complete. Also complete, also complete. And now that I have that level, I can add another one there, and that's also complete. This is complete. That's not complete, because this would technically have to go there. Okay? All right. And now going again, the whole sketchy naming convention, we have the perfect binary tree. So what is the perfect binary tree? A binary tree is considered to be perfect in the case where all internal nodes have two children and all leaves are at the same level. So here, I'll write that. I'll put like requirements. All leaves are at same level. Okay. So a perfect binary tree of height h has 2h minus 1 nodes. And remember, height is the number of nodes from the path from the root to the leaf. So that's the root. That's the leaf. Height of the tree is the longest path that you can find. So like in this one, here, it would be root to leaf, because that's the longest one. If you go here, it's not as long as this one, because there's only one here versus two. So technically, based on this definition, is this a perfect binary tree? This one? Why not?
Because all the leaves are not on the same level.
That's right. All the leaves are not on the same level. Okay. That's right. That's the second part I was going to say. Because here's the thing. Let me fix that first part that you guys were saying. Make this a little bit nicer there. So it was like that, and then it was there. Right? So you said not all the leaves are on the same level. So then I can do this. Now they're all on the same level. But as you were saying, the internal nodes do not have two children. So I would have to make a children here, children here, children here. So what it ends up being is it's just everything is full and maxed out, basically. There's no other way around it. So that's going to be the one where it looks really cool, because it's just like everything's full. So I guess you could say the requirements get a little bit stricter as you go down the list here. An example of a perfect binary tree is the ancestors in the family. Keep a person at a root, a parent as children, parents as their children. I don't know if that example is good because it kind of flips the idea of parent and child. So don't think about that too much. But I think you guys get that. Just basically the complete, even though the word perfect tree is the one where everything is full. Looks nice and rounded, and it's going to be a power of 2, which is why you get that 2 to the h minus 1 concept. Because all levels are going to be like that. Yep.
Is it possible then to have a complete tree or a perfect tree that's not complete? You can't. You can have a tree that's one but not the other, or you could have a tree that's both.
Yeah, but in this case, I think you can have a perfect tree that's any perfect tree will be complete, but not every complete tree will be perfect.
Yeah, that sounds right.
It's like if we draw like Venn diagrams,
Yeah.
the bigger one is perfect. This one is complete. And then let me double check full. 0 or 2 children. That one would not apply for this one. Because this is okay, I think. Mandatory world levels are completely filled except for the last level. Yeah, so
So I think full would be inside perfect, but not
so-
overlapping complete.
yeah, like that. I like this Venn diagram. I should have done that in other classes. Yeah.
I think full and complete can overlap, right?
No, they can't. Because in complete, you could have one kid, but.
They overlap a bit.
That's dangerous. That's dangerous to draw here. They overlap a bit. Oh
There's a
man.
tiny area where
There is, of course.
What, are they gonna graze each other?
Yeah. So what is the Venn diagram thing about that? If they overlap
Venn
a bit,
diagram, that's just a regular Venn diagram. You're drawing like a set and subset.
that's
You're
spooky.
drawing a donut with a hole in it, it's like a hole in it.
Yeah, 2 scrambled eggs.
Alright, that's sketchy.
I feel like this might confuse people a little bit.
What is the overlap?
The overlap is special cases. Like here's a single node. I think that works for all of them. The other overlap are going to be basically anything that's perfect. Yeah, anything that's perfect will overlap on them, I suppose.
Wait.
Yeah, see, that's why I'm like, focus more on this guy. But yes, technically that's okay. Special cases. Yeah. All right. Let's keep going because I want to cover 2 more.
Are binary trees on test next class?
No. The cutoff is quicksort. So yeah. Okay. Ooh, two more things. Let's do degenerate trees first. We already talked about degenerate trees, the linked list. So I'm just gonna write the definition to it. There's another term for them. I don't use this one, but you might want to if you feel offended by the first one. Pathological tree. It's actually less popular, but so
That's it.
is it?
Degenerate and pathological?
I don't want to be called that. I don't want to be called pathological, but I'm sick technically.
No one wants to be called degenerate either.
A tree where every internal node has 1 child. Okay, so degenerate or trees or pathological trees are trees where every internal node has 1 child. So that's like in the case where I have like 1, 2, 3, and 4, and I insert them in that order. It's actually going to create this tree if I just insert them without any sort of balancing. I could also insert them this way. Both trees are correct. Both trees are really bad because, as you can see, they're basically a linked list. And the height of the tree is the size of the tree as well. So n size is your height. So, not good. Why is it not good? Well, because they're not balanced. So let's talk about what balanced trees are. So what is a balanced binary tree? Well, it turns out that a balanced binary tree is a binary tree where the height of the tree is log n. So we consider a binary tree to be balanced if, not when, if the height of the tree is O log n, where n is the number of nodes. Okay? So, remember the height of the tree, you know, you can look at, say, okay, well, from here is 0, 0, then here it's other way around, 1, 0, 2, 0, 3, 0. Whenever you're looking at the height of a tree, you have to look at the height of the subtrees to build up, right? So you got a left subtree and a right subtree because it's a binary tree. And so if you just have a single node, you can consider that to be height 0. And then if you have one node on top of each other, so if you have something like this, well, that's not really sorted, but doesn't really matter actually. Then we can say that this tree has a height of 1 on the right subtree, and on the left subtree has a height of 0. And if you have this node connected to something else, like negative a or something, then this will be a subtree height of 2, and over here, let's say that there's a negative b. Then here we have 0, 0, 1, 0, because you take the highest number of the subtrees and then you add 1 to it to get to the next level. That's the trick. So here we have a tree of height 2. You pick the highest one and you go with that one. And so we're saying that in relation to the number of items on the list, if your height is log n that number, so for example, one, 2, 3, 4, 5, 6, 7. We have 7 here. Let's just throw one more, 8. We are saying that the height of this tree is going to be the log base 2 of 8, which is 3. So 0, 0, 1, 0, 2, 0. Well, sorry, 2, 1. And then 3, 0, 0, 0, 0, 1, 1, 2. You pick the biggest number, and there you go. If that's the case, that property holds true, which is not holding true in this case here because the height is 3, but we only have 4 elements, which should tell us that the ideal height for a balanced tree should actually be height 2. What would that look like? Something like this. Because now we have 1, 0, 2, 1, right? So that way, for 4 items, log 2 of that, that's 2. So that would be what it should look like if it's balanced. But the degenerate tree is not balanced. The height is not that log, and therefore we don't consider balance. So as you can see, the way that I can check for that balance is this little mini algorithm that I'm doing, as I said, where I look at the subtrees and I keep adding +1, and I take the biggest number of the 2. So if I had a tree and I said, well, the height of this tree is 4 on this side, and then 5 on this side. And over here, it's 2 on this side, and 3 on this side. What is the height of this subtree here? What is that number? 4. You take the biggest one of the 2, which is 3, and you add 1 to it. So you get 4. What about on this side? 6. You take the biggest one, and you add 1 to it. And then if this came to some other node, what would be this subtree? 7. And then if this I told you was like 0, there was no children, then this subtree would be just 0, of course. And so on. Is this balanced though?
Wait, you should have 0 on the left side, and then you have 1.
Well, we have no nodes coming out. There's literally nothing coming out of there. So like, imagine like there's not even a line. So it's just 0 nodes. So is this a balanced tree? Of course not. I mean, it doesn't even look right. Like think of when it's even though this is not the best thing to do. Think of it like holding it on the string, and if it looks balanced, like if it doesn't tilt to one side, it's probably balanced. But it's kind of iffy. But that's a good overview. Quick check. Is this subtree balanced though? Whatever goes after that.
Yes.
Yes. And so is this. How about this one though, as a whole? No, it looks balanced. It looks balanced because I just drew that. But technically, there's a difference between here, 4, and 6. So this brings up a good question. What's the threshold? The threshold is going to be this. It's going to be actually based on your algorithm. So the popular one, the one that we will talk about after the test, are ABL trees. So for ABL trees, we consider them to be balanced if the difference, you can do the absolute value of the difference of the left and the right subtree is 1 or 0. So if the difference is 1 or 0, then it's balanced. So here we have 4 and 5, the difference is 1. 2 and 3, the difference is 1. If down here, for example, we had 3 and 3, the difference is 0. However, here the difference is 2, right? You can do like 4 minus 6 and take the absolute value of that, and that gives you 2. Because the difference is more than 1, then we don't consider it balanced. But, you know, I didn't expect you guys to know that because I said that. So. But anyway, that's APL trees. Some algorithms, like red-black trees, are a little bit different.
So is AVL like a subclass of balance tree, or is there like its own?
I would say that APL trees are a special category of binary trees that are balanced. Yes. So I guess the way you said it is right, too. So I'll write this nicely because it's an important thing. Okay, I'll leave it at that. There's also red-black trees that have a similar property. The main difference being that red-black trees are are quicker to insert, but they're not as balanced as ABL trees, which are slower to insert and they're more balanced. So if your data is very insert heavy, you use a red-black tree. If your data is more retrieval heavy than insert heavy, like once you insert stuff, you're good, then I'd use ABL trees. But again, we will spend time talking about ABL trees, maybe red-black trees as well.
Do you mean 1 or 0?
Yes. Or better yet, is less than or equal to 1. And absolute value difference, I suppose, to be very correct technically. So here's the last thing I want to say about this, about balanced trees. So far, when you're looking at something like a array, we have an array. The big things we care about are insert, search, and delete. Searching in a sorted array can be achieved in log n time using binary search. Inserting and deleting is n time. Deleting, you could say O of 1, but you mark something as deleted, but then you break the searching time too. So if you don't want to break the searching time, it's going to remain O of n, right, for both, for insert and delete. With a linked list, there's one more. With a linked list, you can insert and delete quickly in an unsorted one. But when we're talking about sorted data, it takes n time for all of them because you cannot use binary search on a linked list, and because you need to find where to insert before you insert, you gotta find where to delete before you delete. That's gonna all take n time. So it's pretty bad in that sense. However, the power of linked lists is that you can just throw something in the middle without having to resize, right? So binary trees are a combination of both so that you can achieve log n time for all of them. Insert, search, and delete. Because now, if you maintain a tree as a balanced tree, you can insert in log n time because by being log n height, it means you gotta check log n comparisons in the worst case for searching for something. And when you do find that place to search or to insert, if you search or to delete, then you can just append it by making a new child. And if it has a child, then just make a child of that. And again, if it's balanced, you can get to the right spot where you gotta insert or delete in log n time. So you are achieving log n time for all three: insert, search, and delete. So now, this is, I suppose, the best algorithm that you know for storing data. That is fast to access the data, fast to insert the data, and fast to delete the data. Very powerful, like much, much better. You always want to do this instead of using anything else, really. The only disadvantage of this is, I would say, it's a linked list. Well, it's a tree, but ultimately it's like a linked list in the sense that it's all pointer based. So getting the data and printing it is not as easy as an array where you can just access a specific index, right? There's no indices here. So there's that caveat. But overall, this is very, very nice. And there's a lot of overhead with the pointers and things like that. You need recursion to be able to print some of these things out because it's technically a singly linked list. And remember, printing a singly linked backwards requires recursion. So similarly here, you need recursion to do a lot of traversals, which will be the next topic. But yeah, so this is really good. I mean, like, we're improving now. We moved up. Okay, so two more things to cover. The first one is lowest common ancestor. So I'm going to briefly cover this. This is for your own reference. It's not really something that's going to be in the homework assignment. It might show up in the test, though. Lowest common ancestor is, as the name implies, what the common node is, the first common node that two nodes meet up at. So for example, if I asked you what the lowest common ancestor of 10 and 14 is, you would tell me 12, because 10 and 14 share the same parent, and that's 12. What about the lowest common ancestor between 4 and 18? Or sorry, 4 and 12? 8. Okay. Now what if I said what is the lowest common ancestor of 10 and 8?
20.
Not quite. It's actually 8. That's like asking between your grandma and you, what's the common ancestor? Well, your grandma. She's just your like older generation. So yeah. You don't really say your great grandmother or something because you say you share the same DNA as her, at least part of it. So if one of the two nodes you're comparing is a parent of the other one or a grandparent, then that's just going to be your ancestor.
So you are your own ancestor in this case?
You could say that potentially. The lowest common ancestor between yourself and yourself is just yourself. Although that's a little bit strange, but yeah. What about? Well, I was going to do 20 and 22, but 4 and 22 work the same way. What's the answer for us? You said, yeah. Well, you said it right. It is 20, indeed. Because that would be the great-great-grandfather or something. Grandmother. That's all there's to that. Figuring this out in programming is tricky, but if you use recursion, you solve a lot of it. You basically just greedily search to see if one node can find the other two nodes that you're looking for. And if it can, then what was the last place that they both visited, basically. So, like I said, you won't have to code that, but it's good to know. What's up?
If they're ever on the opposite sides, pretty much.
It's gonna be the root.
It's always the other parent or the root.
Yeah, more than likely, yeah. Okay. Finally, the last thing that I want to say, we will eventually cover traversals. And traversals, well, let me put it to you this way. I've been drawing a lot of little circles and lines representing trees, right? Like for the last day or so. That's not so easy to represent in the computer. At least you can represent it with pointers, but like if you're trying to load it in a text file to a computer, I mean, you can like do some ASCII art, but you have to figure out a way to represent the trees in a list format, and then you can build it out of the list. So that's going to be the next thing that we're going to focus on. How to print the tree out and how to build a tree from these list formats. So for example, if I told you that I have a tree, a binary search tree with these four numbers, actually just three numbers, make life easy, with three numbers in it, could you tell me how that tree is made up? Give me one example.
2 is the root.
2 is the root, and then 1 and 3 are the child. Can you guarantee, if I tell you that it's a binary search tree that contains the numbers 1, 2, and 3, that it's going to be that specific style? No, because there can also be 1, 2, 3. There could also be 3, 2, 1. And these are all binary search because they're sorted, right? This is, of course, nice because it's balanced, and these are not. Is this all of them, or is there more?
1 does the root, and then 2, 3.
1, 3, 2. I think that's what you meant to say. And then there's 2, 3, 1, 2. Like that. And it took us actually like 5 minutes to figure this out in the other class because I couldn't remember that last one for some reason. I think those are all the permutations that you can have. Oh, did I not put that one? Oh, I didn't actually. Oh, I did here.
Well, no, if they,
Which one's the parent?
if one,
Or which one's the root? Sorry.
one, and then it has 2 children,
2.
and the other child.
Yeah, but it has to go here because it's greater than. You can't put it here because it violates the rule.
I know you were sorry.
Yes, I am indeed. So permutation versus combination, right? That's the math term, I guess. So anyways, as you can see, for such a small list of 3 numbers, there's this many numbers. So is it correct to say n factorial? No, it doesn't really work. What's the I don't remember, like it's like NC or something.
It's a factorial minus 1. Maybe it's factorial minus
I don't know. I'm scared about saying that because then it works in that case, but I don't know if it's going to generalize well. I think it has to do with that the whole capital C versus P combination versus permutation thing. You know, so what's that? I believe is this permutation or combination? I think it's permutation actually. Anyone remember who's in 351?
It's n factorial over n minus r factorial.
Yeah, that's n factorial over
N minus r factorial.
n minus r factorial. Is this combination or permutation?
Permutation.
Permutation. And what's r? I think R is going to be the repeats. I don't know. I think we just change one question to another one.
Is your total number of objects, and then R is the number of objects you put in a set that you're permuting.
So what would it be the case here? 2?
Well, if your total number is 3 and you're permuting all 3 of them, it would be n with n permute 3. R 3 permute 3, I think.
3 permute 3.
So n would be 3, R would be 3.
So then this would be 0 factorial, which would just be 1. But that wouldn't give us n factorial minus 1. That would just give us n factorial. We still have one missing one.
Well, I don't know if it's actually.
Yeah, I don't know. But anyways, you get the idea. There's a lot of combinations, right? I can Google this and post it on Discord later. But there has to be a better way of representing the tree than just listing the numbers out. And now let me give you another thing. I've been talking nonstop about binary search trees, but you can just have unsorted binary trees. Like I could do something like that. And that's not sorted, but it's still a tree, right? It's back to what I said that day one, that you can make trees to do hierarchy in computer, right? This is your root folder and this is your subdirectories. I mean, in your root folder, it starts with an R. You may have a subdirectory in there that it starts with an A, and inside of that you have a subdirectory that starts with a Z. And it like violates like the search order, but it's still yours. You can do whatever you want. So that makes it even more complicated to figure out, okay, now there's going to be way more combinations than just those 5 that we listed, right? It's going to open up in a whole chain of tons of things to do. More 351 stuff to figure out how many there are. And so ultimately, what I'm trying to get to is we need to figure out a formal way of being able to represent the tree using a list. And so that's going to be your traversals. And we will talk about in-order traversal. We will talk about pre-order traversal, post-order traversal, and then level order traversal, which is also known as breadth first search. And these 3 are, I suppose, depth first search style. At least not all of them, but definitely post-order for depth first search. Yeah, that's more accurate.
Did you need permutation or combination before?
I think I got a mix. So I just want to.
I was just reading it to find it because I think it's combination.
Yeah, I think it's combination, and then permutation would be this one for all mixes like that.
Yeah.
Because this is a special case when they're sorted. So yeah. So it might be like 6 minus 3 down here actually. So something like 6 factorial, 6 minus 3 factorial. Something, I don't know. Like I said, we're going down the rabbit hole that I'm not prepared right now to go through because we got to go over the test. But I will Google this when I have some time later. While you guys take the test, I'll be relaxed Googling this. So yeah, so we need to figure out a way of doing that, and that's where I'll stop about this because going into each of those will take time, but we will, and then you'll know an easy way of doing it. Okay? Any questions on this? Okay, so now we're going to switch over to the 2 topics that I want to review for the test, and then we will talk about the test. So the first one that I want to review is and these are things that we talked about, but maybe I didn't emphasize enough, so that's why I want to emphasize them. And that's a comparison between quicksort and merge sort. Which one's better in which cases? Which one's faster? And so, first thing is, let's talk about the worst case scenario, big O. It turns out that obviously quicksort is slow, it's n squared, versus merge sort is n log n. But that's only when you really screw up. But I mean, technically, we want to have a coverall situation and say, yeah. I mean, yeah, okay, you can say you're not going to screw up, but it's like the Murphy's Law thing. You are going to screw up. So if you're really scared about that, n log n is definitely better than n squared. So merge sort wins that hands down. That doesn't mean that the fight is over, though. If you look here, merge sort, I guess another pro of that is that it's stable versus quicksort that's unstable, and that has to do because of the pivot switching. However, as you will see, something that you will learn in 219, locality of reference is a big thing with cache, and quicksort is much better than merge sort. You had a question, right?
This page is online?
Yeah, this is all on Canvas.
Okay.
Yeah, it's quicksort versus merge sort. I think it's under week 2. I just added it like 2 days ago, though. But yes, this is definitely online under that title. I added it February 21st, so 25th today, so yeah. Okay.
Wait, I thought merge sort does split it in half.
What's that?
Does merge sort split an array in half?
It just not necessarily because of the way the pivot picks items. You may have a case where one side of the sublist is empty and the other one is full, which is the n squared case, actually. Furthermore, quicksort has the advantage that it can be done in place, meaning that you don't need extra space other than the one swap variable, so for you to be able to swap things around. Versus merge sort, where you make a brand new list when you're combining things, and that's why it's stable too. So that is one pro for quicksort. Other than that, merge sort can be parallelized really well. Did I talk about that? Did I talk about polyphase merge sort and how you can not polyphase? Well, okay, I'll jump in there. So with suppose that you have a 2 terabyte file that you're trying to sort, and you only have 1 terabyte of memory. You can't just load the entire file in memory and run quick sort or even merge sort directly because you just don't have the space. Especially merge sort, because with merge sort you need twice the space because you need n space auxiliary versus quick sort just one spot. So I mean, you could probably run quick sort on the 1 terabyte, but not merge sort. So what you can do is you can use polyphase merge sort, which is just merge sort, but taking advantage of the fact that when you split things up, that's fine. You can open each section of the file separately, even in multiple computers, and then separate them. And then as you merge them together, you don't need to have the entire data loaded. You just need to have the 2 pieces that you're merging together. So suppose that you're just merging at the end the 2 1 terabyte sorted files. So you have a 1 terabyte, 1 terabyte sorted file, and you have another 1 terabyte sorted file. You can't fit them both in memory. But what you can do is you can load a piece of this, maybe like a third of this, and then load a third of this, and then open an output file where you're going to write directly to, so you don't have to have that in memory either. You're just writing straight to output as you merge. You might have a little buffer in here to work, so that this is working while this is writing, and that's working in parallel. But ultimately, when you're sorting, if you remember merge sort, you have something like 1, 5, 10, and over here you have 2, 4, 20, and 111. And so merge sort works by having 2 indices point to the beginning of each list, and then you basically get the smallest one and you add it to the output list that you're building. So you get the 1 in, and this moves here, and then you get the 2 in, and this moves here, then you get the 4 in, this moves here, you get the 5 in, this moves here, you get the 10 in, this is done, at which point you just copy the rest of the list here. So, looking at this, I could just load these numbers in memory and not those, and then work with them. And then when I run out of space on this, so for example, I do the 1, I do the 2, and then I do the 4, and now I ran out of space. I can go ahead and load these more on memory to have more ready to go, but I don't need to have them loaded when I'm working on this. Similarly here, I don't need to load the 10 until I'm actually ready to work with the 10, right? So I can load this list in pieces and merge those pieces, dump them out of memory, load more of the list in, merge those, dump them out of memory, and keep going until I'm done. And that way I can basically, merge all of this and this and write it to my output, and then load more of this and load more of this, deal with that, then maybe load more of this because I just needed more first, and then load more of this, and then you're good.
But are you assuming that both of those pieces were sorted to begin with?
Well, yes, because you ran merge sort on those.
Okay.
And so you did the exact same thing before. And this is just the last step. But the steps before probably fit in memory. So you run merge sort on memory with those.
Okay.
You just didn't run the last step because it was too big.
Gotcha.
Yep. You could even run quick sort on it. So polyphase merge sort is very powerful for that regards. And I just wanted to make sure that you guys are aware of it, because in the real world, you're not going to code any of this, but knowing the fact that this algorithm exists and how it works is very useful if you're dealing with big data. The other thing that I wanted to touch on is the lower bound of comparison-based sorting. Because I might have briefly mentioned it, but not really emphasized it. And also because it brings up another point. When you're talking about big O, we always think like worst case scenario, and that's correct, but we kind of assume it to be the upper limit, right? Well, I'm here to tell you that big O doesn't necessarily have to indicate whether it's an upper limit or lower limit, or upper bound or lower bound. That's a better term. It's just saying worst case. In the case of upper limit, we're saying, given the worst possible set of numbers for this algorithm to handle, what can we expect in terms of time complexity? That would be your upper bound. But your lower bound is saying, in general, for this type of algorithms, giving it the worst possible numbers, what's the best that we can do? and the best happens to be n log n for something like merge sort or quick sort, right? You can't ever do better than that with the worst possible numbers given by it. So you could have even an omega that be like the vice versa of this, but that's really rare. If say like the upper bound of omega versus the lower bound of omega, that's kind of weird. It's mostly using with theta and, well, not really with theta, with big O really. So how does that apply here? There's a very important thing that you should know, and that is people have done research and came up with this that said you can't come up with a sorting algorithm that's comparison based that's going to be faster than merge sort in general. So like faster than like n log n time. Yeah, it could be like like a constant faster, but it's still going to be that subcategory. You cannot just make something magically that's n time. That's not going to work. The proof is rather easy once you see it here. Going back to the whole permutation and combinations, think about it this way. Each time that you're checking a number, you're making a decision whether you swap it or you don't, right? It doesn't matter which algorithm it is. It's comparing two numbers and deciding if it's going to swap them or not, whether it's bubble sort or quick sort. Okay, that's a yes or no decision, so that's you could say that's binary. And then for a given list of size n, so for example, if I give you 10 numbers, or not 10 numbers, if I say you're going to sort 10 numbers, but you don't know what numbers they are, they could be in any possible combination. And it turns out that that's n factorial permutations. So that one is permutation I know because it says right there, so I'm okay, I'm confident on that one. So let's say it takes n factorial permutations, and because it's a yes or no answer, you can say it takes base 2 log n factorial. That's the number of possibilities that you could feed your algorithm. And within those categories, there's going to be one where like the list is sorted, and there's also going to be ones where it's like really, really bad unsorted, and it's the hardest one for your algorithm to handle, which is your n, your big O. Okay, so given that, we can write that as saying n factorial is greater than or equal to n divided by 2, n divided by 2, the divided by 2 being, again, because it's a yes or no, binary. And so if we take the log of that, as we were doing before, you can then bring down the n divided by 2 using that property I showed you when we talk about logs. Because when you have something in the sense of, when you have log to x, y, you can bring that y down into y log to x. You can do that. And because you can do that, this becomes n divided by 2 log n divided by 2. That divided by 2 is a constant. We can throw that away. In reality, just n log n. And so in this case, we're saying that it's going to belong to that n log n. And yes, this is in this case omega. But we're still talking about the lower bound. Okay? So the summary of this is basically, if somebody tells you that they can sort something in less than n log n time with comparison-based algorithms, they're lying because it's mathematically impossible. They can use parallel programming to make it faster, but not sequentially. There are other kind of sorting algorithms that quote-unquote finish faster in the sense like bucket sort or radix sort, which are not comparison-based. I don't really have time to talk about them right now. I did in the other class a little bit, so you can watch that video, but because I want to talk about the test. But ultimately, there's always a catch. So there's no free lunch. So you're still going to do much better sorting something with merge sort or Tim sort, which is merge sort combined with selection sort, I think, or insertion sort. One of those two. So, any questions? Okay, cool. No questions. All right, so then test time. Okay, so
That's the exam?
that is the exam.
That's a book.
It's double-sided too. It is 20.
Are you sure that's not like a...
27 pages long. But I do give some space so you can do the answers. So. Yeah. 27 pages long, so I guess this is technically, what's 13 pages? 14
Did the
pages?
TA take it yet?
Just double-sided. What's that?
Did the TA...
Oh, no. the time constraints didn't allow that to happen. However, I'm confident that it should take you an hour because, remember, I used to give one midterm and a final in 302, and that took about 2 hours, which was hardcore for a midterm. So this is about half the material, so it should take about an hour, I suppose. That's my math. That's my reasoning.
Assuming.
That's my assuming. We'll be okay, I think. I mean, there is a class though, so I told the TA show up 5 minutes early so that you can start early, and then give you 5 minutes after at least, or at least until you get kicked out. So, yes.
So they're gonna have a key, because this class is locked.
Yeah, that's a lot.
Yeah, so they should have gotten the Marlowe thing, and I'm kind of worried about that. So they said they did. I don't trust that. So if they happen to not come in and not have it unlocked, any Marlowe card from anybody in the building will open any door. So just ask your neighbor here to open the door, and their key will work. So the TA should know this too. And the TA should, I mean, they told me that. They said they requested it, they said it, but I've never seen them test it, so I'm iffy about it actually. So yeah, you guys can save the day because you're here. Just ask the teacher there to open it, and I'm sure he will. Just you're taking a test, and the TA is cool with what's happening. All right, so okay, I'll take questions after. Let me go over this because I think this is useful information. Actually, no, ask me questions first. Because worst case scenario, I have 2 videos where I went over it. So, do you have questions? Let's go with that. Any questions on anything?
What sort shows up most?
They're even actually. Maybe quick sort. No questions? Then I guess I'll
Should we be reviewing the book or just the lectures?
lectures 100%. Books 0%. Well, I guess it's okay. So let me just go over it then, because I think this will make sense. Yeah. Okay. And like I said, you should watch the ending of the 2 videos that I mean, I will upload this tonight, and so I will the morning one, because I mean, there might be things that I mentioned there that I don't mention here because they ask questions, and that may have extra things that may be useful. So, you know, just put those in the background.
So just to reiterate, you said we don't need too much of the book.
Not really. Everything, my tests come from my knowledge, which is based on my notes, which I may have gotten part of it from the book at some point, but I don't even remember. Actually, I would say I get more from geeks in the book, to be honest. All right, so the original story of the test is that it was 25 questions long. It was too long. I cut it back to 21 questions, and then I added 3 questions back, but they're not 302 questions. They're just 202 questions. They should be easy review questions. So it's technically 21 questions of 302 material. Question 25 is extra credit, so that's why it's 0 points. So, okay. Questions 1, 2, and 3 are the review, as I'm saying. You should be able to do questions 1 and 3. You should be able to do question 1 if you've been doing the assignments. You should be able to do question, and it's a 2-word answer too. And you should be able to do question 3 if you know 135 level C++.
Dang, I don't know that.
Question 2 is hard for programming. That's the one question where you can code or you can just explain it. It was on your 202 final, if you took that with me. And if not, then
That's not a good sign.
it's it has to do with virtuals and classes. So that would be good. Okay?
What was that?
Virtuals and classes.
Oh God, I know exactly what you're talking about.
Oh my, it's the diamond one.
It's like the virtual inheritance.
I mean, if you got your if you have your somebody has a 202 final, because I think you do.
Yeah.
So he's how much you want to pay him for that? Okay. So no, don't upload that, but you can share it. Just don't put it on the internet.
It's the virtual inheritance one.
I'm not. I can't tell you. So
It is. That's all.
no, I can't tell you. So, anyways, question 4. That is going to be like your worksheet where you were organizing things by asymptotic complexity. So like n squared was less than n cubed and so on. So that's just that same question with different numbers, really. Question 5 is your big O and big omega and big theta, explaining what they mean, the math if necessary, or just verbatim. Biggest thing I want to warn you is don't say theta is average. That's not right. You can say typical case. Just don't use the word average because average is a mathematical term that has a very specific meaning.
So what caused the trend?
Anything that's not a math term. Actually, trend sounds mathy. But yeah. Or you could go hardcore with the definition, saying there exists a constant k1 and k2 that limit them, your functions f of x and g of x, which are your big O and theta. I wrote that definition somewhere.
So you said we use the word typical?
Yeah, and the book has a good definition on that, so you can go with that actually. But you don't have to go super technical as long as you explain what it means, and I believe you. 6 and 7 are going to be algorithm analysis. So basically, you can memorize big O, big omega, and big theta and put that answer for question 5. But then questions 6 and 7 are really going to question whether you just memorize or you understand it. So I like to do that. I like to have one question where it's like, yeah, you memorize it, sure, but then do you really understand it? And that's where the real points are coming in. So that's 6 and 7.
And that, and 6 and 7 is specifically for all of theta and.
Like analysis of those kind of things.
Okay.
Yes.
Does 6 and 7 have like, do we have to write a recurrence relation?
No. Recurrence relation stuff is not even here yet.
Oh.
That's near the end of the test.
Oh.
Those are the big point questions. So, question 8 is multi-part, I suppose. It's like the ones where you look at code and you analyze it and you give the time complexity. You don't have to write the recurrence relation for those. You just give the asymptotic complexity of that. Same thing as your homework worksheet, where you just got code snippets. One of the code snippets has a function call to another code snippet, like the homework did. If you get that wrong, okay, so it's like code 4 calls code 2. If you get code 2 time complexity wrong, you lose points there. But then, when you're using that for code 4, you won't lose points for that, because I'll just assume that you're using the wrong one already. So it won't cascade into further problems, so that way you don't lose that many points. So, question 9, yet again, like the worksheet, where you have like, that was a 3-part in the worksheet, where it asks you like, what is the time complexity of inserting into like a linked list or something? Remember that?
Yeah.
And so you have to list your assumptions, which is very important that you do, unless you're listing like the super best case, which is like the popular known one. But if you're saying like inserting at the end of a linked list takes some time, you better say it's because you don't have a tail pointer. Otherwise, you're wrong. Because you could have a tail pointer and make it constant time. So yeah, there's H of those, A through H. The one thing that I want to point out there, because I don't know if the TAs will point it out, is I do my test on latex, and there's a typo on that question, so that's question 9. I forgot to press an enter, basically. So like the question at the end says like, so justify your answer, blah, blah, blah. This doesn't really matter what it says, blah, 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 and assumptions, okay? And then it just says A, it has a parentheses like that, and then here it says, and this is not what this one says, inserting a node into ABL tree, for example, which is not going to be there, obviously. You know, and then you list your explanation, and then there's B, I don't know, something else, and C, right? I forgot to put a enter there and actually space it out. So if you don't look carefully, you might miss this first one, and you just might answer B. Don't miss that. Look, the fact that it says B there should be a sign. There should be an A somewhere. And it's not that I forgot the A. It's just that the way that I got printed, it's there, okay? So just, I'll tell the TA to remind you, but I'm telling you now as well. Once you see the test, it's like obvious that it's, there. But.
So question 9, you said you have time complexity based on those things.
Yes. So it'll be like the worksheet. So we got 5 minutes. All right, I gotta speed up here. 10 and 11, stacks and queues. So there was a question on the worksheet about stacks and queues, kind of like that. Kind of like you have to explain them, like tool 2 stack and queue question, LIFO, FIFO, that kind of stuff. Question 12 is is another big old question, but more focused towards sorting, like this whole lower bound and upper bound thing I was talking about, similar to that. Questions 13 and 14 are more sorting analysis questions. They're concepts of sorting that we talked about in general, not specific to any algorithm. Ideas of that, like stability, in order, space, auxiliary space, all that kind of stuff. Question 15, that's the one that I said was going to be on the test, and it was in the worksheet too. I forgot actually. That's the one where you have a table and you got to fill it in with all the sorting orders we talked about. So selection, insertion, bubble, quick, and merge. And you need to do the big O, the theta, the omega, and the auxiliary space complexity. That's it. You just gotta fill in the table. That's 300 points. If I go back to this, you can see the distribution. Now I'm at question 15, if that ever, yeah, 15. Question 16, now again, so first you list, like the chart that you probably memorized or whatever, but then question 16 asks you questions about that, and so do 17, 18, and 19 about that chart, and actually you really get to explain, like, why is that the case? Like, why is quicksort n squared in the worst case? Like, why is it not a log n? Is that really bad? Like, why? This is where I really see if you actually understand what's happening. Question 20 is going to be like the worksheet where you have a list and you got to sort it and explain how quicksort works, basically. This time, however, it's only 8 numbers long to make life easy. Yeah, I guess I did the classes. I never actually tested it before I gave it to you, so I didn't know how big it was.
It was pretty big.
I probably answered for that out. I probably 4 or 5 times selected all the text that I wrote and then made it smaller, and then selected all the text that I wrote and made it smaller, and I just kept making it smaller.
Like you said, sort it using quicksort, then explain quicksort?
Yes.
That was my question.
Oh, okay. All right. I'm gonna keep going because we have 2 minutes. We have 5 more questions to go through. 21 is the same thing as 20, but with merge sort, basically.
Oh, I get that one.
Yeah, that one is nice because you can just do tree stuff.
Yeah.
The other one you have to do in-place sorting, so you have to know how to use course method or Lamudo's method.
Does it matter which method you use?
I will ask for one, but I won't tell you which one it is. Asking for both is just extra busy work.
Okay.
So what I'll do is I'll ask for one, and maybe like on the final I'll ask for the other
Is
one.
this a most?
I can't tell you.
Yeah, there it is.
I can't tell you. So. All right, 22. All right, so this is where the test gets real. That 22 is like a hardcore question. It's the hardest question in the test. So it's worth 400 points, and it's like the worksheet where you look at a code. Like you look at in the worksheet, it was binary search. You look at it, you analyze it, you get the recurrence relation out of that, and then you solve the recurrence relation. If you get everything right 100% of that question, not only are you going to get your 400 points, you're going to get an additional 10% of the test as extra credit. So that's the motivation to do that right. If you get a tiny thing wrong in that question, though, then you get like maybe 10 points off, but then you don't get the extra credit. So you want to make sure you get a perfect score on that
So I
question.
need a full combo of that one.
Yes, exactly. It's like not only do you get the full 400 points that you need, but you also get the extra 10%.
What is that, like 350 points off?
Yeah.
It could be worth 750.
So like if you don't remember those 202 questions from the final, this will make up for it more than enough.
What were all the parts to that again?
Well, it'll be like the worksheet one with the binary search, where you got to get the recurrence relation out of the code, and then you got to solve the recurrence relation.
Okay.
And then also give the certificate. Yeah. Okay, question, yeah, we have 30 seconds here. Question 23 is just a recurrence relation. So I give you the recurrence relation, I like T of n is equal to something, and I give you a base case, and I tell you to solve it and give the certificate. That's all I ask.
You get the certificate?
Yes.
Wait, what? Can you repeat that?
It's just, you get a recurrence relation, T of n, blah, 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 and then your base case, and you solve it. So we did in class. Question 24 is another recurrence relation. In that one, I also just give you the recurrence relation, and I also give you a base case, but I don't tell you to do a certificate. And in fact, I put that should have been T of 1. I make that base case should be T of 1. The idea is that you can use the master theorem to solve that potentially, so if you so choose to.
So 24 is the master theorem.
If you want to use it, you can also use the other methods too. But I think that'll save you time.
I mean, it's master theorem for everything.
All right, finally, question 25 is extra credit question. That's a 3-part question, 4-2-4, meaning 4 points, 4%, 2%, 4%. First part of that is just something that I talked about in class. The second part is something on the assignments as extra credit. That was in the assignments, and that should be really easy actually. And then the third one is really hard, and it's something that I said would maybe show up on the test, and it will show up on the test. So that is the test. If you have any questions, I'm going to my office, but I will not be here on Wednesday or Thursday. So today's the last day.
Start on the test.
What's that?
What question do you recommend we start with on the test? Start with 22 or?
Maybe like the big point questions, so like the sorting ones, not the recurrence relation one. Wait on that one, because you can just burn all your time on that, and then you're like, wow, okay, I burned all my time on that.
So start with the sorting.
Start with the sorting ones. Yeah. No cheat sheets, no calculators. Make sure you bring a photo ID. They will check your ID.
Yeah, I'm assuming it's this one.
So maybe I missed this, but I'm not certain what you mean by certificate.
So when you come up with a recurrence relation, it's going to be something like 2n plus 1.
Right.
So what I'm saying is that belongs to the class of n. So what constant c has to be to prove that it really belongs to n? Because technically O of n is O of n times c, and that c would be like 3, and n is greater than 1, and then it takes care of that situation. Not 2 because you got a plus 1.
So it's the certificate is the
Oh, I gotta stop recording. Hold on.